Alright, cool. So your boy just got back from work. So I took my sister to school, bro, and I finished these freaking notes. So I'm gonna try to get this video done so I can go to sleep, dude. So let's get it. I only did the LOs that were on, or that that the doc or the PDF said would be on the core 7, I think. So hopefully this is gonna get like hopefully this can get you like through core 7, and if not, like give you the tools to kind of think the questions out, hopefully. And this is just to the best of my ability, and like or just to my understanding, and I did pass core 7 and STA 7. So let's start with LO 7.1. So this is just simply like an introduction to how water splits up. Okay, so splitting up is the same thing as like self-ionization, right? And there's two ways it can be written. So it can be from water splits into H plus and OH minus, or it can be water goes into what's called hydronium, which is H3O, and OH minus, but regardless, they're the same thing. It splits into like this positive part, this negative part. There's a positive part, negative part, right? And kind of a taste, dude. A taste before we get in. The H plus, or just the positive portion, refers to acid or acidity. And then this OH refers to base, reverse to basicity, or just it being a base. All right? So that's just LO 7.1. It's just the introduction of this idea. Next, LO 7.02. So this is going to be your H plus or OH minus concentration and pH calculation, right? So to start, dude, we just got to clarify these square brackets. All it means, or all it refers to, is just the concentration or the molarity of something or of whatever's inside. So the brackets with H in it, it means the concentration of H plus, or just the H plus molarity. OH minus, it would be the concentration of OH minus, right? So the first formula, right? This is going to be on your periodic table sheet, by the way. First formula is the concentration of H plus times the concentration of OH minus equals 1.0 times 10 to the negative 14. Okay? And the questions that they'll ask, it'll be like, what is the concentration of H plus? And then they'll give you like, concentration of OH is like 0.0001, or like 3.0 times 10 to the negative 8, right? And yeah, so I just put like two little notes here. So if you're looking for H plus, so if the question is like, what is the H plus concentration? Then you can just manipulate the formula to get this, right? And all I did here, since we're looking for H plus, right, we're looking for H plus, so we gotta isolate it, or get rid of like, or get this to the other side somehow. So how are we gonna do that? Well, we're just gonna divide, right? So if they're looking for H plus, you can use this formula and just plug in whatever values they give you. Then if you're looking for OH minus, then you just do the same thing, or you manipulate the formula again, and you can use this, right? So that's this first formula. And once again, this is on your periodic table sheet. So it's nothing to memorize, but being able to like figure out where to plug what numbers where, right? But I'm sure you guys can do that. All right. Next is pH. Is this formula. So pH is equal to the negative log of H plus, right? So on your calculator, so you'd have to just input like this negative symbol, log, and then you would put in whatever the concentration of H plus is, right? So if it's like 1.0 times 10 to the negative 3, right? This would be your concentration. And then you would put that into the negative log, right? And you just put that into your calculator, and the answer it spits out will be your pH, right? So, right? So let's see. Depending on the question, if you're looking for pH, you have to find the concentration of H plus and then plug it into this formula, right? So, yeah. So what I meant by this statement, it was just like, so if it'll be like, what is pH when H plus equals like a number, right? So they give you the H plus, so it's like asking for pH, and they give you the H plus, right? So you'd use this formula, and you just, whatever that number is, you just put it into the formula, right? But they could also be like, what is pH when concentration of OH minus equals a number, right? Well, we can see here on our left, the pH formula, you need the concentration of H plus, but the question gives you the concentration for OH minus. So what are you gonna do? Well, you're gonna have to use this formula. Lynn, it's just the extra step. You're gonna have to use this formula, right? Because you need this, and they give you this. So they gave you the OH minus, and you're looking for this. So you do your little calculation, and then you end up with this answer. And now that you know what the concentration of H plus is, then you can plug into this formula and get your final answer of pH. So, yeah, some of the questions, they can have like multiple steps. It's just make sure that you know, just pay attention to what they want, right? And then what they give you, right? So as long as you pay attention to those and just like keep these formulas in mind, and to be fair, they're both on the periodic table sheet. Oh, all three of them, which the third one I'm about to talk about, they're all on the periodic table sheet. So you won't have to memorize the formulas, but just remember that they're very like closely related. So a question might ask one thing, and it would require you to use like 2 or 3 of the formulas, right? So the first one was just concentration of H times concentration of OH is equal to this, and then you can manipulate it various ways, right? Depending on what you need. Okay. And the next one was to find pH, you have to take negative log of the H plus concentration, right? So what if they give you pH and you're looking for H plus? Well, what you would do instead, or what you would do then is you'd take 10 and then you would raise it to the negative pH power. So once again, this is on your periodic table sheet. But just be aware as to like, what are you doing here? So whenever you do this formula, you're finding the concentration of H whenever they give you pH. That might have confused it a bit. But yeah, you use this formula whenever they give you pH and you're looking for H plus. If you're in that situation, then you use this formula, which is once again on your periodic table. So I have some examples here, right? So if they say pH is 7 and they ask what the concentration of H plus is, well, they give you pH and they're looking for H plus. So we're going to use this formula. So we're going to take 10, and they said pH is 7. So we're going to raise it 10 to the negative pH, which was 7. So we have 10 to the negative 7th power. And whatever, like, 0.000 blah, 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 7 you get out. It's not, it'd be, yeah, whatever, the long decimal that it spits out would be your final answer, right? Another one, if pH is 3, what is OH? Well, wait a second, dude. The formula, it's given pH, it only works for H+. What are we going to do with the OH? Well, dude, this is where they get on your nerves because this is a 2-part question. So, you know pH is 3, right? And if we have pH, we can figure out what the H+ is with the formula. So we do concentration H+ is equal to 10 to the negative pH. So pH was 3 again, so that's why it's 10 to the negative 3. We calculate that out, right? And whatever number you get for this, for concentration of H, now we use that into this formula, right? Because we're looking for OH. So we get our concentration of H+ into this formula. You multiply that on your calculator, and then you get your final answer of this. So, very annoying, or it's annoying, or it takes time, I guess. It does take time, but the important thing is that you just, like, slow it down, like, be able to, like, digest what the question is asking, and, like, digest what the question is asking and, like, figure out what you need to do. Because I'm pretty sure, like, anyone could get switched up by, oh, it says pH, but it gives OH. That's not right, dude. Or something's up here. So just take your time. Be aware what these 3 formulas can do and what they can give you, because they're very strongly connected, right? Yeah. Okay. So that's for LO 7.02. Okay. So next, wait, I'm pretty sure there's some practice tests on LO 7.2 as well. Let me check that really quick. Practice bonus sets, blah blah blah. Yeah. There is a 7.02 practice test on Blackboard that you can use to, like, practice this. All right, cool. Now I can move on in peace now that I know it's there. Next LO, we're talking about the pH scale, right? So just a general idea. So pH ranges from 1 to 14. It can really go from like 0 to like 15, but this is like the main, what most stuff is like talking about, right? So smack in the middle of that, we have pH of 7, which is neutral or water, right? If it's less than 7, so 1 through 6, it's acidic. Greater than 7, it's basic or alkaline. All right. So how do you tell if something is neutral, acidic, or basic? Well, we use the formula for pH to find the pH, and then we can tell from there, right? There is also a risky shortcut. I guess, like, maybe if you do like a lot of practice, you might notice it. And it's just that if the concentration of H+ is greater than the concentration of OH, it will be acidic. If there's more OH than H, it will be basic, and if they're equal, it's neutral. But once again, this is kind of risky. This trying to find the pH and do the calculation is definitely the safer route to go, though it might like take time because you might have to like convert from like they might give you like OH, but and then you just have to like convert using the formula to find the concentration of H, and then plug it in. So it might be a little time consuming, but this is definitely the safer bet to figure out the pH, right? And once again, LO 7.3 is just the pH scale. So is it neutral, acidic, or basic? And there is a practice test on 7.03. This is a big part of the exam too, or of there's like in like the later half section of the Core 7 exam, you'll get to a point where it's like, oh wait, no, I should save that for the end. Okay, just ignore what I said. So 703 pH scale, 1 to 14, 7 is neutral, less than 7 acidic, greater than 7 basic. And how do you find the pH? You use the pH formula, which is also on your periodic table. And for practice, there's a 7.03 practice test. Alright, now let's move on. Alright, dude. Let's get to the annoying part now. We're talking about acids. Okay? So, what is an acid? So, an acid is a compound, or it's just a thing. Yeah, it's a compound that can donate or release H plus ions. Okay? And they're usually written with an excuse me, with the H in front of the like rest of the symbol. So like H2SO4, HCl, HF, H2S, HCO3. They all have an H in front of it. So it's very like so it's kind of like a giveaway that it's an acid, right? So there's some classifications between them. So now we know what an acid is now. Now there's some classifications. The first one being strong versus weak. Okay? Because there's going to be questions on the test where they'll be like, is this a strong or weak acid? Is this what's the other classification? Is this a mono or polyprotic? Whatever. But we'll get there. But first, we're just talking about strong versus weak. Okay. So strong acids are listed on the periodic table sheet. And I believe it's these three: HNO3, HCl, H2SO4. Those are your strong acids. Everything else, weak acids are literally everything else. So if it's not these three, it is weak. And then I guess if you want like the additional information as to like the differences between strong and weak, strong acids, they completely break down. So they have this, whenever you write them out, like HCl, it'll split to H plus and Cl minus, right? Yeah, but it has like just this one directional arrow because that's what strong acids do. Weak acids, on the other hand, they're in equilibrium, so they have like the two-way arrow, right? So yeah. One more note. So like strong, since this like they only have the one-way arrow, if you have a certain concentration of one thing of a strong acid, you'll get that much, or that same concentration, but of the H plus ion. But I'm not sure if that's on Core 7 or not, but I guess good to know type thing. Also, something to kind of be aware of that I'll come back to later. You see how this is H2S, and like when it goes through, it drops into H plus and then HS. So acids, whenever they like process or whatever, it's only one H. But we'll get there. I'm getting ahead of myself. But the important thing here, strong versus weak. Strong acids are listed on the periodic table, these ones. So if it's not one of these three, it will be a weak acid, which have the equilibrium sign. So yeah, cool. There's also another thing to be aware of. So there's functional groups, remember from like 2B, so these are like your ketones, aldehydes, blah, blah, blah. They're weak acids. There's 3 of them. There's 3 functional groups that are acidic, and there are all weak acids. So which groups are they? Well, carboxylic acid, right? Acid's in the name. This is a weak acid. Phenols, so the hexagon with the OH, this is an acid, or considered an acid. But be careful, because that shape, it needs to have the double bonds. If they just show you this, it's just a shape with no like lines inside of it, but there's a OH, this is not a phenol, so it is not acidic. All right. Thiol, right? This is not one that like we had to remember, but they might just say thiol in like the test somewhere, and if you see this, then you know it's acidic. All right. So yeah, strong versus weak. Strong acids are these 3. Everything else is weak. And then there's 3 functional groups that are acidic that you should be aware of: carboxylic acid, phenols, and thiols. All right. Now we can move on to the next classification, which is monoprotic versus polyprotic. Okay? So don't get too tripped up here. We know what these prefixes are. Monoprotic means that there's only one H in the front of the acid. So like HF or HCl, there's only one H, and there's only one H. There's no subscript. So that's why they're monoprotic. Polyprotic means there's more than one H in front. Okay? And then this is kind of split into 2 more. So diprotic and triprotic. And I'm pretty sure we've seen this before. So diprotic refers to 2 H's in the front. So like H2SO4. There's a 2 here. And then triprotic has 3 H's in front of it. So like H3PO4. All right. So, and the reason why it's important, or like how this will be on the test, is they'll give you something and then they'll ask like, is this monoprotic, is this monoprotic, is it diprotic, or is it triprotic? And you just have to check like one of them, right? So yeah, this is kind of like using some older concepts, but it should be a little not too difficult to wrap your head around. And here's like an additional note. I swear I saw it. It was like one question. It'll be like, of like of these like different levels, right? Which is the strongest acid? So like the strongest polyprotic acids have the most H's. So what's that meaning to say is like, as like, okay, how do I say it? So like if we take this example of H3PO4, right? So each time it goes through and like processes to become like an acid. Okay. No, I think we'll come back to this. We'll come back to this. So we'll stay here. So for just a recap, monoprotic versus polyprotic. Monoprotic, 1 H in the front, so HFHCl. Polyprotic is more than 1. And what are the 2 categories in subcategories in polyprotic? we have diprotic, which is 2 H's, so H2SO4 or like H2S. And then triprotic, which has 3 H's or like H3PO4 or like H3ASO4, right? There's a 3 here, right? Simple as that. So that's it for acids, right? So what's the other thing for as opposed to acids? Well, it would be bases. Woo. So, what is a base? So this is compounds with OH, so like NaOH, KOH, or compounds that can accept an H plus ion, right? So the OH ones, these are just like dead giveaways to being bases. But the one that might not be as obvious would be the ones that can accept the H plus. So what are examples of this? First, we have ammonia, NH3. So when NH3 is combined with the H plus, you get NH4 plus, right? You see how like the H plus like added to here, right? It's a H plus acceptor, right? So that's why you have NH4, a positive charge, right? Next are amines, which are kind of very similar. They have the nitrogen, basically, right? So here is our amine functional group, right? And then we have H. And then once again, it has to accept the H. So the H will go to the nitrogen, right? And now we have this. And yeah, now we have this little like format, right? Oh, I forgot to add the plus here. Because since, oh, that's it. Because we gained a hydrogen, we also get like the charge like becomes more positive. All right. That still looks like an X. Let me fix that really quick. Okay. Hopefully that's better. So, yeah. So amines, like this structure, you can always add a H to it, which is why it's a base. They can also be written in this format though, where they have like CHO with like numbers and like there's an N. If there's an N, you know that it's an amine, right? So this H can just simply go here, right? But the thing is, if it's written in this like compressed form, the H will just go into the front. Just like, yeah, the H will just move to the front. It's, it might make a little more sense whenever we get to like a later LO. But yeah, if there's a nitrogen present, it's a base because the H plus can go to the N or to the nitrogen. All right. Last category, or last example of a thing that can accept the H plus ion would be hydrocarbons with a negative charge. So if it's like a so like if it's a CHO with like big numbers or whatever, and it has a negative charge, right? That just means it can accept the H plus, right? Because H has a positive charge, positive 1 charge, and they get balance all out. And remember, the H will always go to the front. All right. So those are samples of a base. You have the ones that say OH in them. Anything with a nitrogen, right? Or a hydrocarbon with a negative charge. All right, so that's what a base. So that's what a base is. I'm sorry, dude. I'm getting sleepy. I'm trying my best. If it turns out a little like confusing or bad, just text me. You guys should have my number because I'm gonna text this to you. So yeah. Alright, classifications of base. Strong versus weak. So strong bases are these two, NaOH and KOH. And I didn't even finish the sentence. They completely dissociate, right? Similar to like strong acids, they have like the arrow. And then weak bases, just like weak acids, exist in equilibrium, right? So once again, these are like your nitrogens. And I think, yeah, I forgot to put the hydrocarbons on there as well. But yeah, it's just that they have this equilibrium thing. So strong bases are these two, and anything else would be a weak base. Okay, so here we go. And here's the last part of the bases that we might need to just to like be more careful with. So where will the H ion attach to the base? So right, so if it's a OH, if OH is present, OH will attach to the H plus, creating H2O, right? So if it's NaOH, right, with plus H plus, or plus H, okay, then we'll have just Na ion, so Na plus 1 ion, and then water, right? Because the H was accepted to the OH here. And those two led to water, leaving this by itself. Okay? If NH3 is present, you simply just add the H. So once again, nitrogen, and there's a H, we just add it, right? And we have NH4. If it's an amine functional group, just add the H plus to the nitrogen in the same way, or similar to NH3, right? So this is our amine functional group, right? Dang, I did miss a lot. And we're supposed to add H plus, right? And you see, H plus, we'll add it here to the nitrogen. And now we have this, this is the new, this is the result of the base combining with the H ion. Okay? I forgot to write about the hydrocarbons, so I'll write it really quick. So, okay, here we go. So if it's a hydrocarbon with a negative charge, place PLACE. I'll just erase it real quick. Place the H in front of symbol, and then add +1 to charge. Right? So we'll do a little example here. So if it's like C2H3O negative plus H plus, this will lead to HC2H3O. Right? So all we did, we put the H in the front, and then we added 1 to the charge. So it now has no charge because -1 plus +1, they cancel out, right? I'll just put another one just to clarify. If it's like C6H10O2 minus plus H plus, well, we're going to put the H in the front again, rewrite the original hydrocarbon, so CH10O, and then add 1 to the charge. So -2 plus 1 would be just -1. All right. All right. So that's for bases. So that's what a base is, or that's what is a base, how to tell if it's strong or weak, and then where to put the ion, or where to put the ion to the base. Right. Now we'll move on to acid-base dissociation, or like their breakdown, and this idea of a conjugate pair, which we've kind of done conjugate pairs, except we just didn't give them the name, right? So, but we'll get into that. So let's start off with the acid properties, right? So when an acid breaks down, it splits into one H ion and the original acid, but we subtracted a H plus and we subtracted 1 from the charge. So that was kind of a lot of words, so I think it'll be easier to show in the examples. So here we have HCl, a strong acid, right? And it broke down into one H plus, or into an H plus ion, and then Cl minus, right? So what happened here? So we took the H away, right? So it could be an acid where it's a H donor. And then with the Cl, right? We subtracted the H, and then we also subtracted 1 from the charge. So before it had no charge, now it has -1. Let's look at H2S. H2S, right? So we removed one of the H's, right? So we have our H plus ion. And because of that removal, now we just have HS. So we subtracted one of the H's, so HS. And then we subtracted 1 from the charge. Before it had no charge, now it has -1. And the same idea just goes for even HSO4 with a 2- charge. It's just once again to further, or just to get more practice of that transformation, right? So we subtracted the H, right? We have the H plus by itself, and then we're left with ASO4 2, right? It's now separated from the H, so we're gonna subtract 1 more. We're gonna subtract 1 from the charge, and we have 3-. Right. So the transformed original acid, so the one where we subtracted the H and subtracted the charge, that's what's called the conjugate base. All right. So acids, so the acid is paired with the conjugate base, right? So why is it called the conjugate base? Because it is now able to accept a hydrogen, right? So if we look at this compound, H2PO4, right? We removed the H plus, so we subtracted 1 of the H's and subtracted 1 from the charge. This is the conjugate base. Okay? And because it's the conjugate base, we can also do the backwards reaction here, where the H plus is now being accepted, right? So that's just where it gets the name from. But the idea is simply, if you have an acid, the opposite, or what's on the other side of the acid, the conjugate base. All right? So here, H2SO4, we drop 1 of the H's, and this is our conjugate base. Yeah. All right. And then one more note. So the conjugate bases of weak acids they are considered weak bases. Okay? So like let's look at an example. So HF, excuse me. So whenever it splits up, we have the H ion, and then we have F by itself, F minus by itself. So HF is not one of the listed strong acids, so we assume that it's weak, right? So we have that equilibrium sign. So since this was a weak acid, that means F minus is a weak base, right? Meaning it is basic. Like in regards of like the pH. The pH would most likely be higher than 7. And the reason for this is it'll be one of the questions on the test. But that's why I'm just trying to convey that idea, right? So let's look at another example. HS minus, right? This is not one of the strong acids, so it is a weak acid. When it goes through, we subtract the H, we remove the H plus, and we're left with S2 minus. So this is a weak acid, and this is the conjugate base of the weak acid. Therefore, S2 minus is a weak base, meaning in regards to pH, it would be basic. And then last example here, HCl. HCl is a strong acid because of that arrow. It's listed on the periodic table. Yeah, that just means, but since it's strong, this Cl minus is simply neutral. It doesn't do anything because, once again, it came from a strong acid. And it's only the weak acids that make weak bases, weak conjugate bases. Right, so that's for acids. So the big idea here is acids are paired with conjugate bases, right? So if you start with the acid, you'll end up with an H plus and the conjugate base. So acid goes to conjugate base. So now we're gonna kind of reiterate the idea this time to bases, right? So bases are H plus acceptors. So when H is supplied, the original base, it now gains an H and it adds 1 to the charge. So essentially the opposite of what happens to an acid. So this might be a janky example. So let's look at this. So S2 minus, right? That's our base because it can accept the H plus. So whenever we're going to add a H to it, right? We get HS with the minus. Right? We added the H to the original thing, and then we added 1 to the charge. It was -2, is now -1. Right? Similar process it goes here. So here we have a hydrocarbon with a negative charge. The negative charge means that it can take up this H with the positive charge. So we're just going to put the H in the front like this. And since it now has a H, we can add 1 to the charge. So it was previously -1. It is now no charge. Right? And yeah, here's just another example. This time it's a hydrocarbon, but we see that there is a nitrogen here. So whenever it interacts with the H, you simply just put the H in the front, right? H is now in the front here. and then we add 1 to the charge. So it was previously no charge, is now +1. All right. So very similar to how the acids were. The transformed original base, right? So we put the H in the front and then we add 1 to the charge. It now becomes the conjugate acid, right? Because now it has H plus that can be donated, right? So like in our example here, right? So for the base of S2 minus, the conjugate acid is H2S, or is just HS minus 1. I'm sorry, my speech is getting slurred because I'm getting really sleepy. I'm really sorry, but I hope this turns out well, so I don't have to re-record and get it like to you guys later whenever we only have like 2 more test days. So I'm just trying my best, dude. Alright. For this example here, right? Our original base was C5H7O2 minus, and our conjugate acid, right, is the H, is the same thing but with the H in front, right? So HC5H7O2, this time with no charge, right? So it's just the mirror version of the acid idea. Same thing with the pH scale. So conjugate acids of a weak base become weak acids, right? So F minus is a weak base, right? So its conjugate acid, its conjugate acid would be acidic. Here we have NaOH plus H plus H. NaOH is one of these strong bases, right? So when it goes through and it makes Na ion with water, the Na ion is just neutral because it was a strong base, right? So just to reiterate the main points for basic properties, so bases will go to conjugate acids, right? And weak bases leads to a weak conjugate acid. Simply to say, it would be acidic. All right. Yeah. I did try to like write out the notes into more like sentence like things so it'd be easier to come back. Because I think I realized, or I think I saw something from a prior notes thing, and I wrote it in the way like that I take notes, and the way I take notes is like very like super simple, not very kind to the reader. So I hope these like sentences kind of make more sense, especially since I'm like really slurring my speech trying to get this over, or trying to record this. I'm sorry. All right, next LO, the idea of amphiprotic species / compounds. So what does amphiprotic mean? All it means, it refers to the ability of a compound to act as both an acid, so meaning it donates H, and a base, which means it accepts the H, right? So we can look at water. So water as an acid, we can produce H plus, right? So it can go through this reaction where it creates H plus, and if it's a base, right, Well, H2O can combine with H plus to make this hydronium ion, right? So it simply has the ability to be on both an acid and a base. Here's another example. This is bicarbonate or hydrogen carbonate, right? So as an acid, it can go through and it can donate the H that it has and leave you with CO3 2 minus as the conjugate base, right? And then here as a base, well, HCO3, right? It still has that negative charge, so it can accept the an H ion to make H2CO3, right? And then the last example here, it's a structure example, right? We have an amine group here, so that's the base, and we also have a carboxylic acid here for the acid part. So when it wants to act as an acid, it can give up the H that's right here, right? So now we have H plus and the same structure, but this time, oh, I should make it more clear. At the end, back when it was an OH, it is now an O negative. Yeah, there we go. That's a good one. So, yeah. So this is what it was before. It is now this. O negative because we donated the H for an acid. For a base, on the other hand, right, we have this nitrogen amine group, and the H will simply just go to the nitrogen, right? And we have this. This is the same structure, except there is now an additional H on the nitrogen. So, yeah. Was it amphiprotic? It could be both an acid and a base. And I put a little shortcut here. And if it's a symbol, if it has a H in front and it has a negative charge, or it has a negative charge or a nitrogen present, then it would be amphiprotic. So like HS, there's an H in the front, has a negative charge, amphiprotic. HC5H8N, there's a H in the front and there's an N. This is amphiprotic. HSO4 minus, there's a H in the front and it has a negative charge, amphiprotic, right? So just look if it has an H and a negative charge or nitrogen somewhere, it would be amphiprotic. Or at least I would default to it being amphiprotic. It is a shortcut, so I'm not too sure as to how well it goes, but I do use it, so yeah. And if it's a structure, you look for the amine group and the acidic functional group, right? So amine group, once again, it's just anything with a nitrogen. The acidic functional groups listed were phenol, thiol, and a carboxylic acid. So I have examples of those here. So here we have the phenol, and here we have the amine. So it has both, amphiprotic. Here we have the amine group. Here we have the thiol group. It has both the acid and base side, amphiprotic. Here we have amine group. Here we have carboxylic acid group. They're both there, acid and base, so it is amphiprotic. So that's LO 7.11. So now we'll move on to the last one that is supposedly covered in Core 7. Hold up, give me a breath. All right, let's do this and knock out. I'm so excited. All right, 7.12, buffers. So what is a buffer? Buffers are a combination of acids and bases with their conjugates that resist a pH change. I'm pretty sure this is additional information or supplemental information, because I'm pretty sure the question they ask is how to make a buffer, or like what is needed in order to make a buffer of blank. So in order to make a buffer, you need the original acid or base plus its conjugate. Okay? And if you have these two pieces, right, you will make a buffer. So let's look at some examples. So if you want to make a HS minus buffer, we need HS minus and the conjugate. Yeah, the conjugate base for it, S2 minus. And be careful, because sometimes the answer choice will have like this HS minus attached to something. As long as, like, here you have, it's Na and then it's like Na and then HS. So when they split up, you know that this is going to be, like, this will be Na plus, and you know this will be HS minus, right? So even though it's not HS minus like by itself, it will still create it. So just be careful, because they might, for the answer choices, this might not be on there, but this might be. But it could be this NaHS, which would essentially just do the same thing. All right? So be careful. So when making a buffer, make sure you have the original as well as the conjugate. So if you want to make a buffer for HCO3, well, you're going to need HCO3 and its conjugate, conjugate base, CO3 2 minus. And here, we made a basic buffer, right? So base, it's a hydrocarbon with the nitrogen, right? So you're going to want the original base and then its conjugate acid, right? So we added the H plus 1 to the charge. So this is the conjugate, right? And both pieces are needed to make its buffer. All right. And that should hopefully be all of the notes for Core 7. I strongly hope that it would be able to get some of them. Ooh, here, I do have a sample question. Here. So, okay, there's kind of a lot. Okay, but this is one of the questions that like came to mind when I was taking the notes. It'd be like, check all that apply for, and it would give you like one of these, right? And then these would be your options. Like monoprotic, diprotic, triprotic, weak acid, weak base, strong acid, strong base, or amphiprotic. And they're like, it's not like just select one, it's like check all that apply. So we can just do one really quick. So like let's look at these two, right? Oh shoots, my dog is barking. But okay, I'll just do this really quick. HF, right? It's gonna be monoprotic. It's gonna be a weak acid. Can't be a weak base. Can't be a amphiprotic. It is not. H2S, diprotic, weak acid. That's about it. F minus. Weak base. That's about it. H2PO4. H2PO4. Diprotic, weak acid. It can also be a weak base, right? Because it has a H in the front. It's negative, meaning it's... Hold up. Let me zoom out a little bit. H2PO4, diprotic. It is a weak acid because it's not one of the strong acids listed. It is also a weak base because you can see that it has a H in the front. It has a minus sign. Wait, let me organize this better in my thought. For this, you see the H2 diprotic. Yeah, you can see that it's also a weak acid, right? Because of the H in the front. And then you can also see it's amphiprotic, right? There's a H in the front and it has a negative charge. So it can be both an acid and a base. And it's definitely not going to be a strong base because there's strong bases is just NaOH and like KOH. So it's not one of those. So it has to be a weak base, right? So this is one of the questions that come up, but also do practice test 16 on Blackboard because that is like literally half of the unit of the Core 7 exam, right? So I hope this helped. I'm gonna try to upload and send this as soon as possible, maybe when I wake up. But yeah, dude, I wish you guys the best, and text me if you have any questions, right? Dude, good luck.